my name is Isaac Bears from Bears Science Lab, and today we're going to be looking at a pretty interesting problem where we have a convergent sequence of sets. Let's say we have A1, A2, A3, etc. Infinite series of sets such that their limit is some set B. So it might look something like, and our assumption is AN is always a subset of AN plus 1. So it might look something like this is B, this little blue strip is A999, this little red strip might be A90, this little blue strip might be A20, this little red strip might be A5, and so on. So the subsets grow and grow and grow, but at some point their growth kind of curves off, and it approaches this limit set B. Now here's what we're going to prove. We're going to prove that the limit as I approaches infinity of M of this union is equal to the measure of B. How do we justify that? Well, let's look at what's going on here. You might be tempted to say first, well, this is just the measure of the limit as I approaches infinity of this union. And of course this, since AN is a subset of AN plus 1, that implies that their limit set, the limit set of their union is just B, because this union should just be equal to AI. AI contains AI minus 1, AI minus 2, and every other set in the union. So that union should naturally be equal to AI. So this should be M limit I approaches infinity, AI, and B. Now that would work, but there's one crucial flaw in this reasoning. This limit doesn't commute with everything. Now, just to show you a little example, you might remember a very funny proof that people were trying to claim was real on the internet from a very long time ago. So, you have a circle of radius 1. You take the square, you take a square and draw it so that it encloses the circle. I think there's got to be a better way. Okay, something like that. That works. No, there's got to be a better way. Okay, that's good enough. So, the basic reasoning is, now you fold in this corner over here, so it looks like this. You fold in this corner over here, so it looks like this. You fold in this corner over here, so it looks like this. You fold in this corner over here, so it looks like this. The perimeter of the resulting shape has not changed. Just for extra effect, I might as well erase the parts that were originally there. So as you can see, the perimeter has not changed, but the shape has gotten closer to the circle. Then it proposes you fold again. You subtract these little bits. And so you erase these. And it starts to look more and more like a circle, but the perimeter has not changed. Then you repeat the process again. You fold here, 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 here. And as you can see, the shape is starting to approach a circle, but the perimeter has not changed. And so people reasoned, well, the perimeter of the square was always 4. So the perimeter of the circle, which is its limit, should be 4. But we know that the perimeter of the circle is 2 pi, which is proof that pi is equal to 2. Now that's unfortunately not how it works. Oh no, the perimeter of the square is 8, I just realized. So this was a proof that pi was seemingly equal to 4. Because what people were misunderstanding is that the limit of the length of the shapes is not necessarily equal to the length of the limit of the shapes. The limit of the length of the shapes was always 4, even though the limit of the shapes was a circle, so the length of the limit would be, just be 8. So the length of the limit would be 2 pi. People couldn't understand that even though the limit of a plus b is equal to the limit of a plus the limit of b, and the limit of a times b is the limit of a times the limit of b, it doesn't commute with every operation. The limit of the length of the sequences, the limit of the length of the sequence was not equal to the length of the limit of the sequence, which shows that since pi is not equal to 4, we actually have to justify what we're talking about when we swap out limits that way. So, how do we do this? Well, the way measure is defined is that the measure of a plus b is equal to the measure of a plus the measure of b, subadditivity. And we can use that to our advantage. So now, think of what this actually looks like. Sure, you can say that it's just AI. This is the limit as I approaches infinity of MAI. Now, you can actually say that. You don't need the limit to say that this is AI. But then, how do you go about making the claim that this is equal to this? Well, here's what we're going to do. We take m of ai plus 1 minus m of ai. Now, this is going to be equal to, of course, since ai is a total subset of ai plus 1, this is going to be equal to m of ai plus 1 without ai. So now, what are we going to say here? Well, as I approaches infinity, wait, but how does that help with argument? How can we swap it? Wait. Hold up. Okay. So, how can we break down the limit as I approaches infinity of m of ai? What is m of ai? Well, it's the measure of the most recent growth plus the measure of the growth that happened before that. Wait, no. plus the growth that happened before that, plus the growth that happened before that, plus the growth that happened before that, and so on and so forth, until before you know it, you have the first growth and the original set. So you can break it down into this sequence of sets. Really, what you're doing here is writing the limit as I approaches infinity of the sum from n equals 1 to I of m of a n without a n minus 1, the nth growth, ending with the last growth, the ith growth. Oh, that sounds like I have a lisp. So, now what do we do with this? Well, you have to realize that as you increase this, you're going to be adding progressively smaller and smaller terms. So this is the sum from n equals 1 to infinity of m an minus 1. But now, realize that we have subadditivity, which is the most wonderful thing in the world, because subadditivity allows us to say MA union B is equal to MA plus MB, and that works with infinite unions too. We can say MU from I equals 1 to infinity AI is equal to the sum from n equals 1 to infinity of MAI. So we use this as like a vehicle for the limit to infiltrate our measure, because the measure doesn't necessarily work well with limit, but then when it's disguised in the form of a sum, it allows the sum to walk right in, like a Trojan horse. Wait, no. And then you realize that this is just equal to what? The limit as I approaches infinity of the union from n equals 1 to I of an without an minus 1. And then you realize, crap, the limit has infiltrated our measure. It dressed up as an infinite sum to get inside, and now it's able to break down our walls, because this is just by definition AI. And so that's MB, completing our proof.